All right. Anyway, yeah, it's a pleasure to be back here. Spent a lot of time here, so glad to be back. Let me start with extending the ideas Dan laid out, basically in how to characterize the proton. And as he said, really, it's an extension of the Rutherford scattering going back a century. And we tried to set this up. What's I find rather interesting about the inclusive deep and elastic scattering is that you measure the outgoing lepton, the energy and the angle, E2 and theta in this notation. And from that, you have a set of equations that can get you to the X and the Q. That is the Q squared, the energy of the photon, and the X, the Burkhead X, we're going to relate that eventually to the momentum of the protons inside. So it's a beautiful measurement. You don't have to measure anything about the hadron, which is good because that's complicated and messy. But by just measuring the energy and the angle of the outgoing lepton, you can get this information. And for reference, I've got a couple other common deep and elastic scattering variables here. Nu is the energy difference, and Y is the inelasticity. And sort of traditionally, they thought of this as you've got a lepton current and a hadron current, and they interact via photon. And in terms of Feynman diagrams, they're drawn there. So I have the amplitude on one side, and I want to go from the amplitude to the cross section. So I'll square that, and that gives me the mu structure. And the lepton tensor in blue is that's entirely calculable because that's fundamental things that we know about. It's electrons, muons, photons. So that's purely calculable, but it's this green blob down here, the hadronic tensor, that we can't calculate. That's got the very complex non-perturbative QCD, all the things happening inside the proton or the nucleon that you're dealing with there. And so the cross-section will be amplitude squared, and it'll be this L mu nu, W mu nu. And that's what we have to struggle with. And as Dan laid out for you, how do we do this? Well, we basically parameterize our ignorance. We don't know how to calculate this W mu nu, but we can expand it out in terms of Lorentz structures. And so G mu nu, P mu nu. And I've also got this object here, a W3. Notice these first two are symmetric with respect to mu nu, but this third one is anti-symmetric because of the epsilon tensor, and that's going to give my parity violation. So if I'm only looking at photons, I only need 1 and 2, but if I start looking at things with parity violation like W's, that'll pull those in. And so historically, we use the W notation, but then we converted to the so-called scaling structure function, these F's, with this notation here, and then that's your cross-section. And again, these F's just parameterize our ignorance. We don't know what these are, we can't calculate these, but we're going to try to measure them. And so, but let's back up a bit, and what's all this scaling we've been talking about? And Dan showed you curves like this. This is an older one where this is the measurement of the F2. And ideally, this is a function of X and Q. But what you see here is I've plotted it for a wide variety of Q squared values, many different experiments, measurements over a wide variety of Qs. And they all seem to lie along this universal scaling curve. And so it seems like, to a good approximation, this seems to be independent of the Q, independent of the energy. And what does that tell you? And just to reiterate what you heard this morning, if you have an object and it doesn't depend on the resolution, you shine a photon on it and you do a low energy, low resolution long wave a photon, and it seems to be, have no structure, and you crank it up to high resolution, it still has no structure. And here's the structure function over here. I've written it as 1. That seems like a point particle. And that's very suggestive. Let's contrast that with something that's not a point particle. Okay, here I shine something with a low energy, dim light flashlight, and I crank up the flashlight a little bit, and it seems to have some structure. And look at that, we discovered the Higgs. Wow. So okay, and here a little bit more realistic. Dan gave you the classic experiments, but again, when you look at the atom, at a long wavelength, it seems to be atomic, seems to be fundamental. That's where the name came from. And you look a little further, and it starts to have some structure. You see the electrons and then this hard core. and you look a little harder, and then inside the protons, you see these hard marbles, these quarks, and that's the pattern. And so the scaling feature, when you see something's independent of the energy, that's giving you a clue that something's going on there. And as he alluded to, this is an approximate relation. Here's a wealth of data, including the HERA. It's got SLAC NMC, BCDMS, a variety of things, including the HERA. And if I pick the right X, this is the structure function versus Q. If I pick the right X, it's absolutely flat, independent. But if I go out to the extremes, of course, that has some variations. And in fact, we're going to be looking at those later when we go to higher order corrections and things like that. So that's the background. And I want to underscore, we are not yet at the parton model. I've not mentioned the parton model at all. We characterize the hadronic structure function in terms of its Lorentz structure, but we've not used that at all. And so here's the form that Dan had before. And let me just take the limit, this is the hadron mass here. If that's small compared to the characteristic energy, target mass, if it's a proton, it's a JeV. If I'm at a couple JeV, that'll be small. So let me simplify that. And I'm going to do this for neutrino deep inelastic scattering. And that's because for that case, I have a W exchange. So I have a left-handed coupling, left-handed current. For antineutrino, you just swap. I've gotten this, I've converted the F123 in terms of the F123 in terms of helicity structure function. So plus is right, minus is left, and 0 is longitudinal. That's going to be convenient for where I'm going. And so here it is in terms of the helicity structure functions. And what stands out is what you see in terms of this is that the right-handed one has this factor, kinematic factor 1 minus y squared. The left-handed one has nothing, and the longitudinal one has a function of 1 minus y. Okay, and here are all the conversions, and you can work that out. And we'll do the neutrino because that's nice. It only has left-handed couplings from the weak interaction. The antineutrino will have right-handed so that you swap left and right. You could do the photon, but that's going to have a sum of them, and it just makes it a little bit more complicated. So now let's line that up with the parton model. Okay, and so here's my simple parton model. I'm going to start out with the proton as just a bag of free quarks. Okay, up, up, down. Let's start with that. And then my parton distribution, that is the probability of finding things inside the proton, I'm going to write it like this. There are going to be 2 up quarks, and each one carries a third of the momentum of the proton. And there's 1 down quark, and that also carries a third. And that's a nice, simple expression, and it conveys what we expect there. But of course, that's not the whole picture. We've got all these nasty gluons coming in. And those gluons can connect things and smear things out. They can also make quark antiquark pairs. But the key element that we're going to use here is the fact that the scales involved in our hard interaction, that is the scale Q, is much higher than the characteristic scale of what's going on in the proton. And the characteristic scale of what's going on in the proton, we'll label that as lambda QCD. That's a few hundred, maybe 200, 300 MeV. And typically, the scale we're doing the measurements on are high energy. At HERA, we can get up to 300 GeV. At fixed target, we can get maybe 30 GeV. And because of that, because of the inverse relationship between the interaction time and the energy, if I come in and hit this parton with a very high energy photon, I hit it so hard and so fast, I kick it out of there before it has time to make a phone call to any of the other neighboring quarks or gluons. And so because of that, I can say that the probability of finding that is independent of whatever I'm doing this. If I'm scattering, if I'm probing it with a photon, a W, a Z, whatever, because I'm doing that so quickly and it doesn't have time to interact, it doesn't have a chance to say, look, here comes a W, adjust. Okay, so it's that separation of scales that allows me to do this simplification and say, I'm just going to model the proton as a bag of stuff with certain probabilities of finding up quarks and down quarks, etc. And that's the factorizable picture that we get into. Okay, now when this energy starts to get not quite as high, and they can make phone calls, we've got other corrections to worry about. In fact, at the EIC, quite a lot of their interactions are in the range of lower Q, where you do have to worry about those things. But we're not going to worry about those here. So in that approximation, I can do this calculation. I can put all that very messy hadronic physics into this blob here, and I'll just say I'm going to parameterize this as, the proton produces a quark A with some probability, and then that will interact with this photon, and I can calculate that in the standard model. And I'll write the total cross-section for the physical process as this probability times this theoretical calculatable part. And so this I can measure from experiment, this I can calculate from theory. Where does this come from? I have to deduce this. I measure this and basically unfold this. But because it's supposed to be universal, it's because it's not supposed to depend on the specific process, I can do that in a universal manner. I can put many experiments together and get that out. And we'll do that in just a minute. So let's keep going with this. And so F tells me the probability of finding things inside the proton. That'll characterize the proton. And it may have some quarks, Q, it may have some antiquarks, Q, and just for fun, let's suppose it has scalar objects, okay? And we know there's up and down and who knows what else. So let's just calculate and see what happens. A little bit of homework. The convolution is the proper way to multiply probabilities. And so you can try it with a coin flip down here and work it out. Also, it's a symmetric function in these lower cases where it's not obvious it's symmetric, but if you drop in the delta function, it is. So you can look at that. So the top line is what we got just from using sort of Lorentz considerations. And then if I go and calculate with that simple model with an assumption about quarks and antiquarks and scalar guys, I get this. And again, what's nice is because I've chosen the neutrino case and only has left-handed components, if I did the photon, it would have a sum and it's harder to decompose. But you look at this line and look at this line and say, gee whiz, it seems like this right-handed structure function tells you something about the antiquarks. The left-handed one tells you something about the quarks, and the zero component, zero helicity longitudinal one, tells you something about the scalar quarks. And it's that correspondence that we go from, matching up these mysterious structure functions that we don't know about and lining them up with the quarks. Okay, and then of course you can do this for photons and other things, but in this simple case, what I have purely a left-handed interaction, that's what I've got. In fact, you can sort of see because the quarks have a left-handed interaction, they give you the left-handed helicity structure function, antiquarks give you the right-handed, and then the scalar gives you the longitudinal, okay? And you may not have heard about the scalar quarks inside the proton. That's because we went and measured them, and there aren't any. So we know about the quarks, we know about the antiquarks, but as far as we know, there are no scalar fundamental objects inside. So that means this longitudinal structure function is zero. And if you go back and see the relationship between these helicity structure functions and the 1, 2, 3, this is equal to the difference between basically F2 and F1. And the fact that this is zero, which is the longitudinal structure function, says that F2 has to equal this. Okay, so this is the Cullen-Gross relationship. And when people write this down and say that's the Cullen-Gross relationship, I look at that and to me that doesn't mean anything fundamental to me. But when I say, hey, that means the longitudinal structure function is zero because there are no scalar quarks inside the proton, that means something to me. And so I find that useful. So let's dig a little deeper. And they've actually gone and measured this longitudinal structure function. Okay, and I fibbed a little bit. It's not exactly zero. Here's the Hera measurement of it. That was actually a very complicated measurement. They had to run the beam at multiple energies to get that. But it turns out that this is at leading order at zero, but it does have corrections. For example, there's corrections due to the quark masses. Basically that, you can violate helicity with masses. So you get a correction there, but also at higher orders, you can have an alpha S times a gluon and a quark piece, and here the gluon has a big role. So this is very effective at getting at the gluon distribution. And so that's quite important. And in fact, that's one of the key measurements to try to get the gluon distribution, alpha S, and the evolution. So let's come back to the PDFs now. And with my toy PDFs, these are nice and simple. Okay, I can calculate those very readily. The up quark is 2 times it says the momentum fraction in each one of those is a third. The down quark is 1 times a third. And let's check some quark number rules and quark momentum sum rules. So if I integrate this, the delta function gives 1. I find out there are 2 quarks, 1 down quark and 0 strange quark. So, all right, that checks with our expectation. Let's check the momentum sum rule. Okay, so I'm going to multiply that probability times the momentum fraction x, and that'll give me the momentum fraction. And let's go, and we find out the up quarks are carrying 2/3 of the proton momentum. The down quarks are carrying 1/3 of the proton momentum, and that's good. We've accounted for all the proton momentum. So we go to the lab and we measure that, and what do we find? Oops, it doesn't add up. Okay, if you go and do that, okay, and you go to Slack and you measure it, you don't get 100%, you get 50%. You're missing half the boat. What's going on here? And that was the clue that the quarks are only carrying half of the momentum. What's the solution? There aren't any scalar quarks. We already ruled that out. Turns out they're gluons. They're gluons inside there, and the gluons actually carry about half the momentum, but because they don't couple with photons in the simple leading order picture, you're not going to see them. And so that's how they deduced that the gluons were there. All right, so the gluon, now we got to put the gluons in. Here was my simple PDFs. Everything was at a third. Okay, and I put the gluons in, that smears things out. But in particular, they're going to kind of, you have this, they go off to infinity at low energy. That's because, as Pavel showed, if you go to low Q, your alpha S gets very large. And that means at low energy, it's very easy to emit a gluon. And so you've got lots and lots of soft gluons. Maybe at some point they fill up the proton and saturate. That's a topic the IC is going to look at. But those are going off to infinity. And that's going to give you a problem now, because if you come back and do the quark number sum rule, it's going to, the quark distributions diverge like something like 1/x and 1.5. You try to integrate that, you get infinity. And the problem is you can't just integrate the up quarks. You have to, because it's very easy to create up and U and U bar pairs, you'll have an infinite number of U's, but also an infinite number of U bars. And it's only the difference that's conserved. And so if you compute the difference between the two, then you will get it. And in fact, we're going to try this out on Thursday. We're going to do some Python exercises with some PDFs. You'll compute the number sum rules, and hopefully you'll verify that our PDFs satisfy those. So, and again, we neglect saturation. At some point, it should saturate, and something's got to happen. You've got recombination or saturation, something's going to happen. So, and again, Aurora Couture will do the PDF tomorrow, so I just want to connect up with that. But here's the rich structure of the proton. The up, the down, and the up valence is about twice the down valence because there are 2 up for every down. And then if you go to low momentum fraction, the U bar, the S, all these things start going up. And here's the gluon. I had to divide that by 10 just to get that in the picture. Okay. And then I talked about scaling, but if you look at a scale of 10 Jeff squared at a 10,000 Jeff squared, you get very different results. And so this scale violation is an essential feature of the QCD and something we definitely have to take into account. Where do the PDFs come from? This I took from the particle data group structure function review. And in the XQ plane, you see here the fixed targets down here. So those are typically at lower energies. We like to do it in Q squared. I guess that's historical reasons. But Q squared of up to 100, so that's Q of 10. And then here is this large area here. The Tevatron is up here, and then the LHC covering out there. And basically, you take various experiments, Strelian, deep inelastic scattering, WZ, jets, TT bar, you put all those together because these are supposed to be universal. And then you take those measurements, you do the calculation and invert it to get your Parton distribution. Okay, and we can do that only because it factorizes. That means we can mix TT-bar JETS WZ with DRELIAN and DIS. For the DIS only, here's a summary of those. And again, the big one here is HERA. That really extended our reach in X and Q. That was the first collider for lepton hadron. And that ran 92 to 2007. And here's a flash of the two detectors, the H1 and the Zeus detectors. What's on the horizon is the electron ion collider at BNL. And so here's a aerial shot of BNL. Here's the AGS ring where Cronin and folks discovered CP violation. And then the RIC ring, currently there's two rings that are colliding nuclei there. They're going to decommission one, and then they'll take the nuclei and add a separate electron ring. And this can go to 275 for protons, and they'll have an 18 JeV electron ring outside of that. RIC operations will finish at the end of this year because they have to start dismantling the unused ring for hadron and start installing the EIC facilities. And here, in terms of the XQ plot, again, Q squared X, this is the reach of the EIC for various, this is the maximum reach, and you can also kind of crank down the energy a little bit. And in the FITs, we'll get to that later, but typically we like to make hard cuts in the Q. We like to stay at relatively high Q, so we have this factorization and don't have to worry about the non-perturbative things. We also have a W cut out some of the high X where there are other non-perturbative things. And you see that actually leaves a lot of the data on the floor. And as I sort of illustrate here, are we looking under the lamppost, just because that's where it's easy when the interesting physics is somewhere else. And one of the things we hope to do at the IC is extend this a little bit. Look at high X where you have to deal with all these things. Look at low Q where you've got the non-perturbative physics, and also be able to press down to low X, particularly with heavy nuclei, to see things like shadowing and recombination. So that's what's on the horizon, and we'll hope to see some of that. Now here's some homework. You can go and verify this. For example, if I look at the F2, you see the F2 for electron-proton scattering. It's basically just charge-weighted, you're measuring the quarks in there. It's a charge-weighted distribution. So the up and charm are charged 2/3, so that's 2/3 squared is your 4/9, and your down and strange, that's 1/3, 1/3 squared is a 9th. So it's just a charge-weighted distribution. The neutron is the same thing, swapping the up for down. And then here, what's interesting is the neutrino, because that's a W scattering, that probes either the down or the U bar. And you putting all these together, you can basically get different linear combinations to determine the independent combinations that go in there. Even before we had the parton model, there were various sum rules. You can see these are typically from the 60s. These were discovered actually before the parton model. You can link this to the parton model. And so, as I say, before it was invented, they noticed these relations. Then you can go back, and if you kind of work out, use the info on the last slide, you can sort of verify that sort of makes sense. This one in particular is quite useful, and we'll use that when we come to the strange analysis. How do we distinguish flavors? As I showed you, when you're probing things with the photon is sensitive to electric charge. So the up quark charged 2/3, that has a factor of 4/9. The down is 1/3, that's a factor of 1/9. So if you're measuring a proton, typically you're more sensitive to the up than the down. And if you look in the measurements, if you look at the air bands of PDFs you'll see tomorrow, you'll see that's true. So, that's great, but how do we get the other ones, particularly the charm and the strange? Well, we can use the W boson, and that's good because I can, if I do a W minus, I'm sensitive to the U, and a W plus is sensitive to the D. They come in with equal weight, and I've taken the Cabibel angle 0 to keep things simple. And then for the Z boson, it's a combination of the vector and axial vector currents. And basically putting all these together, as you saw in the previous slides, I get different linear combinations, and then hopefully I can disentangle those to figure out what's going on. But it's going to be a series of measurements. Also, I can use different targets. I can use proton, that's the easiest. Unfortunately, it's kind of hard to get a neutron target. That's you go to the stock room, say, give me protons, no problem, but we're out of neutrons. JLab has done some interesting tricks to do that. They've done deuterium, tritium, but you can also look at nuclear targets and take a look at that. But then you have to worry about the nuclear corrections. And so, if you're going to do this instead of a proton, if you're going to do it on an iron or lead, maybe the distributions are different in iron and lead than a proton, and you have to account for that. Now, there's one rumor about where the nuclear corrections came from. Somebody said that they dug this up by Fermilab and it's got proton, iron, and lead data, but I don't know if that's true or not. But if you work it out, and this is an old plot, if you say to a good approximation, the nucleus is just a bag of protons and neutrons, loose, and you just sort of use isospin to get the proton to neutron and put them all together, and that's my model of the proton, model of the neutron, model of the nucleus. You're pretty close. You're within about 10%. And so this ratio, this is the ratio of iron, which is close isoscalar, to its deuterium, but we're going to pretend that's isoscalar. Basically, that model gets you within about 10% of the right answer. These deviations, you see, it's about a 10% deviation, and there are various regions here. This is the fermion motion, where the momentum gets close to 1. And in fact, in nuclei, you can all the partons can sort of conspire to push one of those above 100% of an individual nucleon. You've got the EMC effect region that was first found by EMC. There's a shadowing region down here at small x where it seems to be less than 1, because maybe the partons are shadowing one another. And then there's the anti-shadowing region, which you have to come up with a model for that. We fit this. I'm not sure how well we understand this. There are various attempted models to explain this, but we can fit this. And when you apply this, when it was applied historically, what you would do is you would start with neutrino data, which typically was done on heavy targets. As Dan showed, the CFR NUTAV, basically they cut up 700 tons of a battleship and stack the iron together with scintillator, because neutrinos have a low cross section and you need a big target to do it. So you've got iron and lead, a very heavy target, and you want to correct it for isoscalar, you want to correct it back to proton, and then you put that in your global fit. And again, when we first did this, we sort of took this curve as absolute and didn't modify it, but that's not quite correct. You have to have interchange or communication between the two. And there's a branch of CTEQ that's doing that. Basically, the NCTEQ or nuclear one is doing that. So we've incorporated this in. So basically, the nuclear PDFs can communicate to the protons, but also vice versa. And you put it all together and try to get the nuclear correction. That's made some good progress, but there's still a number of puzzles outstanding. And this is one of them. I refer to this as the split personality puzzle. If you go and you do charged leptons, so that's photon exchange. You can do that on light nuclei. That's not a problem. The photon, the charged leptons have a high cross section. But the neutrinos, they have a very low cross section, so you have to do those with heavy targets and then correct those. And when you go and get this nuclear correction, one gives you the red curve and one gives you the blue curve. And that's very curious. So this should be something universal. This should be something universal, and they should be the same. And so we've puzzled over this quite a bit, and people have looked at this. As Dan mentioned, it's challenging because much of this data is old, and there are not any high energy, short of the EIC coming on, there are not any high energy neutrino DIS experiments in the future. We may have to wait for the EIC, and hopefully this can shed some light on it. But again, this is one of the challenges you have to come up with, and that's a standing puzzle. But you can compute here's the proton, this is the gluon and the S quark. For the proton here in the lead, for a variety of nuclei. So you can see as you go from A to 1 to A to 208, how those things change. And you can get the whole range of nuclei for that. Let me switch to evolution for a little bit. And this sort of to motivate this, I pulled up this preprint from Charles Hodgson, but I think this is Alice talking to the Cheshire cat. And it's good to remember that you have to pose your questions very carefully because often the answers depend upon the question. So she says, Cheshire Push, would you please tell me which way I ought to go from here? That depends a good deal on where you want to get to, said the cat. I don't much care where, said Alice. Then it doesn't matter which way you go, said the cat. Oh, so long as I get somewhere, Alice added as an explanation. Oh, you're sure to do that, said the cat, if only you walk long enough. And so when we ask what's inside the proton, it's important that we pose the answer carefully. Because if I say what's inside the proton, it goes back to that scaling question. If I shine a very dim light on it, it looks like a point object. And then I look a little closer and maybe it's two up quarks and a down quark like that. But as I start to probe more and more, I find that, gee, there are these gluons floating around. And if I probe a little more, I might find some up quarks, and the gluons can make a up pair. And then if I probe further, I get downstreams, etc. And basically from the uncertainty principle, I can sort of cheat on the energy by delta E if I do it for a short enough time. And so I can make charm antiquark charm, even though it seems a little bit counterintuitive. You put a proton on a scale that weighs 1 GeV, but there's a probability of finding a charm anti-charm in there, even though it weighs more than the proton, and a probability of finding B in top, and all sorts of things. In principle, if you look closely enough. So you have to keep in mind your question, and that's where the scale comes in. So you say, what's inside the proton? And it's very dependent on that scale. So when I do my calculation, here's my cross section, and it depends on X and Q. Those are the variables I can measure in my DIS case. And I've got the parton distribution, the probability of finding various partons in there. And I've got sigma hat, that's my Hart-Scatterdian cross section. But when I divide this up, I'm going to try to calculate this perturbatively, and I'm going to sort of sweep everything else under the rug inside these PDFs. And I have to draw a line between those two. Okay, and the line I draw between those two is this mu scale. And mu it's an energy scale just like Q, and as Pavel said, will go back and forth interchangeably. But Q is the physical energy of the photon. This mu is this artificial scale that I use to divide these in two. And so what you see here is that the two quantities on the right-hand side, they both depend on mu, but the left-hand side is independent of mu. And what that means is this is going to be measured by experiment. They give me a number, but the way I divide up my calculation should not depend, CDF or Atlas shouldn't get a different number if I do my calculation in a different way. But if and you can see here in the cartoon, if I pick a large scale, okay, so this is a high energy, and then I'm going to absorb all this junk into my proton, or medium scale, I'll put that gluon out and absorb this in, or small scale. As I go back and forth, I'm trading contributions between the two, and I've got to count for that. So mu comes in here, mu comes here, but it does not come in here. And so one of the interesting things, we can use this to figure out how the parton distributions change with energy scale. And so what we're looking for is we're looking for DF d mu. Let me just check on. All right. And in fact, here's a result. I just plotted these up. Here's the up quark, and if you go at low scale, you get the red curve, and high scale, you get the black curve, and I've taken a selection in between. The same for the down. You see a bump here of about 1/3 because, again, it's a valence quark, and same for the down, because they're supposedly primordial up and down quarks in there. But for the gluon and the strange, these are all generated perturbatively from gluon splitting the QQ bar. But so that's an example of the evolution. what's sort of interesting is to look, you can calculate the momentum fraction of the different pieces of the proton as a function of scale. And so here it is, if you go down to low scale, the gluon, as I said, takes up about 50%. And here's the up quark and the down quark, and there's about twice as much up versus down. And then D bar and U bar are pretty close. The strange is down a little bit. And then, I've got charm and bottom that come on. And, if I go up to high energy, maybe you can imagine I've got an issue 3 symmetry or not quite. And maybe if I go to, huge scales, I can get issue 4 or issue 5 scale. And we'll calculate this on Thursday with the Python stuff. But let me show you a sort of quick and dirty derivation of this. And so here's the parton model. There's the experimental cross-section sigma, the parton distribution F, and instead of writing sigma hat, I'll write omega because the hats often get lost. So this omega, this is something calculable from my standard model because that will also link fundamental particles. Sigma is experimental, and then F is the non-perturbative object I'm trying to figure out. And so what I'm going to do is I'm going to invoke the renormalization group equation. And that's a mouthful, but basically all it means is that it says the experimental cross-section does not depend on how I divide it up. I chop F and omega, I cut that in half with some U scale, but the physical result does not depend on that. So I'm going to apply the chain rule, and small detail, I've taken the Mellon transform to get rid of the convolution, hence the tildes, but we'll let that slide. I'm just going to apply the chain rule and have df omega, f d omega, and then I put all the f stuff on one side, all the omega stuff on the other side. And in your math class, when you see that before, you say, gee, what I do there is I separated variables. How can it be that, this mu dependence equals this mu dependence? The only way I can think of is you set them both equal to some constant. I'll call it gamma. Okay. And what's neat about this is on the right-hand side, everything here is perturbative to be calculable. On the left-hand side, that's completely non-perturbative. Okay, but because I can calculate this and use a renormalization group equation, I can calculate gamma. And because I can calculate gamma, I then know how how this parton distribution changes with scale. And so if I just rearrange this, here's my differential equation, Gleason Mellon space, and then I can solve this. The answer is F, the energy dependence is mu to the minus gamma. Okay. And then if you convert that back into the Mellon space, back into normal space, this is your D-Glap evolution equation. This gamma is called the anomalous dimension, and that may seem unusual, but the motivation or the link of that comes from, it's a dimension because mu is, of course, energy scale. So it's the, it's the mass dimension that F scales with, hence the word dimension. And it's anomalous because if I had perfect scaling, that is, if they were really point-like particles and did not depend on energy, that would be 0. Okay, and so that's what it is in Mellon space, and then you map it over, and you have these splitting kernels that give you the evolution of those. But that's essentially the link between the two. So let me check where I am. Okay. Some details, if you want to try the Mellon transform, you can try that out in a simple function. And then with the evolution, basically what you're doing is you're sort of adding up towers of diagrams like this. You're saying, when the parton comes from the proton and goes in here, it can do all sorts of gluon radiation, and that can change the structure of it, and it looks something like this. And this is the equation, and these are the splitting functions. It tells you how, when you have a quark propagating along and emits a gluon, say how things change. And so, so you can, work that out. You can just do an expansion of that, and that's where that comes from. You'll see that again tomorrow in the PDFs. If you want to work out some details of this, or just look at this for reference, here are a few of the splitting functions. And I've labeled the momentum in red here. So in this case, the quark starts out with momentum 100%, and it goes here with momentum x, and what's left over is 1 minus x is carried away by the gluon. You see there's a singularity 1 minus x because that if that gluon gets soft, you get the singularity that Pavel was talking about. One note here, you have to read these backwards. For example, the P here, the PQG, you read it backwards. So this is the splitting function P for gluon going to a quark. That's the convention, you read it backwards. And here it is gluon going to a quark. This one is symmetric in x and x 1 minus x because of course they're the same. Here again, this is a quark going to a gluon where the gluon has momentum x. You see the singularity is always the gluon that gives you the singularity. And here's a gluon going to two gluons. You have a singularity in x and a singularity in 1 minus x. And then if you want to work those out, some exercises, you can do a little practice with the plus distribution function. That's how it's defined. And then here's the here's the other splitting function. It has pieces like this, both real diagrams and virtual. And then the gluon has pieces from individual gluon loops. That's CA contribution. And then quark loops is a TF contribution. And you can look into that because if you add enough quarks, for example, you can flip the sign of your beta function and you can get unconfined QCD for enough quark flavors and few symmetry limits and things like that. Yeah, I'll leave it there. So quick recap so far, we've gone from the Rutherford scattering, we've computed electron-hadron scattering and connected up that to the parton model. And we talked a little bit about factorization, how the PDFs are independent of the process. And that's what allowed us to mix things like we could mix DIS and draw the AND to extract the PDFs. But they're truly not scale invariant because there's this evolution that comes in, but we have a handle, thanks to the renormalization group equation, we can calculate the anomalous dimension or calculate the splitting functions and find out how they evolve with energy. Let me wrap up with just a few more things. Of course, you can take this to higher order. So you can go from leading order, and then at next leading order, you may have a gluon process, and then a extra gluon and things like this. And you can calculate all these things. Some of these have been done fully, some of these approximations. What you see here, this is up to next leading order, this is exact, the higher orders are approximate. What we see is for F2, things are pretty stable. F2 is pretty stable, but FL is not, because again, at leading order, that was almost zero because there were no scalar quarks. And so we got a little bit of contribution from implicit relation from the quark masses from the gluon, and particularly in some of the extreme regions, you have to worry about that. So if you want to get the longitudinal, if you're using that to get, say, the gluon or the running, you have to get that high production at high precision. Let me next go to the strange quark distribution, because this is actually what we're going to do tomorrow in the tutorial. So we talked mainly about the up and down. Where do you get the strange from? That's a problem. The up quark, that's that's plus 2/3. The down and the strange have the same charge. So the strange sure looks a lot like the down. And if you're trying to measure the strange underneath the down, that's going to be a real problem. How can you get at that? Well, with the neutrino experiments, they found a rather clever way to get at that. And what you do is you take a neutrino beam on a nuclear target, and in the case you get an S quark here, you can turn that into a charm, and the charm will decay semi-electronically about 10% of the time. And you have the same process of a down going into an up, but the difference here is the charm is heavy enough so when it decays semi-electronically, often it kicks that muon out, so it's isolated. And so you have an isolated muon here and isolated muon here of opposite signs. And what you do is you count the number of dimuons versus the number of single muons. And in a oversimplified theorist picture, that gives you the number of down quarks versus the number of strange quarks. Even better, if you can go to Fermilab and you have a neutrino and antineutrino, a sign-selected beam, you can do the same thing with the anti-quark. and then you can measure those individually. Okay, and in fact, that's what they did. And again, this, when we do this, we have to worry about the nuclear correction because, these are done on heavy targets. So we've got this split personality. And, when we got strange results for the strange distribution, we were worried about that. But then you go to the Large Hadron Collider. And so here's the Tevatron. And you see this is W production of the Tevatron here. It's mainly UD, but at the LHC, the CS can be, sort of 20, 30%. And so you might be able to use that. And in fact, that's what Atlas did. They took advantage of the fact that, the W and Z have a non-trivial amount of strange in them. And in particular, the W is linear in the strange, whereas the Z is quadratic in the strange. And so by looking at the ratio of those, you can extract information about what the strange should be. Now, we talked a little bit earlier about SU3 symmetry between, say, the U bar, the D bar, and the S. And maybe in a simple world, you'd expect SU3 symmetry, but then you step back and say, well, the S quark is heavier, so you would expect it to be sort of suppressed relative to U bar and D bar. And the fixed target experiments typically found that to be suppressed by about a factor of 2. That is, the S or S bar, doesn't matter, was about half of the U bar or D bar distribution. And that's what they measured the fixed target. But when Atlas went out and did this measurement, not only did they find that they not only found that it was SU3, they actually found the S quark was about 120% of the D bar, which was very surprising. Now, I mean, this is 2017. There's been some progress, and that's been reconciled to some extent with the CMF measurements. But this was very surprising because, if anything, you expected at most to be 1. You didn't expect to be greater than 1. And so this was a puzzle, but, and what's the answer? Well, we're going to try this tomorrow. Okay, so we have this was done in the original was done in Xterra. We have the data for that, and we're going to try that. And we're going to run it. We're going to open up the fit and see that sure enough, it prefers something above 1. And then you can play around with the parameters and see if you can reconcile this and get something that's a little bit more normal. So that, as I say, is part 1, the case study, the strange case of the strange PDF, and that's on tap for tomorrow. So here's the recap so far. Let's see. And I will end it here. But again, we went through connecting from Rutherford scattering and the layout that Dan did for us. Connecting the lepton hadron the way we sort of parameterize our ignorance. We connect that up to the parton model, the simple parton model, and then we went beyond that, talked about scaling behaviors and how we can do the evolution, the energy dependence of that. And hopefully that'll be connected up tomorrow when you have the PDF lectures. And then we'll save the resum. We'll save the resum for the Dralian case. But that's where we're going. So let me finish there, and we have a few minutes for questions before we go on. Thank you. Okay, and if there are none now, we'll have the evening discussion also. Okay, let's take normally we have 4 lectures plus tutorials today. Today we do have a special one. We have a special lecture on quantum computing. So let's start that in about 10 minutes, a quarter of. So why don't we take a short break if you want to think the coffee room's open if you want to grab a quick snack or something, and be back at quarter of, and then we'll continue with the final lecture of the day on quantum computing, just something a little bit different for you. Okay. All right. Thank you.